Hello to everyone. My name is Marianna Belotti, and today I'm going to present you the work entitled Game Theoretical Framework for Analyzing Blockchain Robustness, a joint work of three different universities: CNAM University, Avignon University, and Sorbonne University, all of them, of course, from France. Okay. As you may understand from the title, the work I am going to present you combine distributed system, in this case blockchains or more generally DLTs, distributed ledger technologies, with game theoretical analysis of rational users' behavior. The work aims at first at understanding the risks in applying and implementing blockchain technology, and secondly, we want to analyze and formalize these risks. In the end, risks are summarized via indices that can describe the blockchain risk level, representing, of course, blockchain robustness. So let's start by giving an idea of what blockchain is. I'm sure that every one of you has heard about bitcoins and blockchain technology in general. But let's give a brief definition to understand the concept. A blockchain is a distributed ledger having a blockchain architecture. Transactions are collected in blocks that are chained one to another. These blocks of transaction compose the ledger that is distributed among different nodes of the network that are nothing more than users of the systems. Nodes store a copy of the ledger and update it with new inputs that are, of course, new appended blocks of transactions. Nodes or users write on the blockchain proposing a block to append. This proposition is considered valid and the block is officially published on the ledger if users of the blockchain agree on a common vision of the ledger, finding an agreement or consensus among them. If blockchain are complex system characterized by complex protocol, things become even more complex when different blockchains or different chains interact. Our contribution analyzes and formalizes risks for blockchain and layer 2 protocols as well. We'll see later what layers 2 protocols are. So yeah, I'll show it now. So layers 2 protocols are indeed protocols enabling different blockchains, like this one, the green and the yellow one, to interact, or different chains. You can see the pink and the orange one interacting with the main chain, that is the blue one. In this case, we talk about side chains. Okay, now let's try to understand what the risks of deploying blockchain technologies are. The risks of a blockchain derives from the fact that the distributed ledger is made by different users that we can call node actors, or agents, or after we will call them players that act rationally, trying to get the best for themselves. When these agents are presented a protocol, they can follow it or deviate from it. Deviation consists in attacks to the system that can be advantageous for some users or not advantageous for others. Hence, it is important to model users' behavior through game theory. Game theory allows to understand the action of blockchain users and to analyze the robustness of the system by looking at equilibrium. Formally, rational users participate to a game that is a tuple composed by a set of players, a set of strategies, and a utility function, able to evaluate the player's happiness. Players have available different strategies to choose and can evaluate them with a function that in this case called U. We have Nash Equilibrium. A Nash Equilibrium, whenever given a strategy profile, no player gains more in deviating unilaterally. Equilibrium represents, of course, stable solutions, making all players happy. We can understand now that it is important to have strategies recommended by blockchain protocol that are Nash Equilibrium if you want to have a stable system. And making all of our players happy, and this, of course, means that we will have a system that won't face attacks and will be robust. Okay. All of these concepts of risks and protocol can and should be formalized and will be formalized by our model. This will be done by wisely combining distributed system theory and game theory. Our approach for deformalization is not to find a particular attack configuration and generalize from that, so something from that one, but it's actually the opposite. We identify all possible behaviors of users and all possible scenarios that, of course, make sense with respect to the blockchain protocol we are analyzing. Once identified outcomes are evaluated and equilibria are identified. Let me show you what I'm talking about with some pictures. A blockchain protocol looks like this. Instruction to be followed at any decision step, blue instruction if the protocol is followed, and purple instruction if not. And now let's move to a game theory representation from game theory. So we have now a branch, the right branch representing users following the protocol and reaching the final outcome. And we have also branches on the left representing outcomes if users deviate. In this case, we have no payment, so a phrase, but we can formalize it and associating a numerical value to the outcomes to measure the happiness of the users. So here, the formal definition of a game tree, where we can see that it simply represents what we previously shown. Of course, it's easier looking at the picture with respect to reading this definition. And okay, a question: why do we have on this as outcomes values -1, zeros, or ones? This is because we assume that 0 corresponds to the utility of every user in the initial state not participating in the protocol. Then we assign a negative utility value for outcomes where a user is less happy than he or she was in the initial state, while positive values are assigned to users with more utility than the one in the initial states. And we selected 1 and -1 for simplicity. Okay. Now let's combine a bit game theory. Users can be now called players, and distributed system theory, and formalize any blockchain protocol as a mechanism. That is a pair of a game representing the situation, so the blockchain system, and the strategy, sigma, representing the prescribed protocol to be followed. Now we see that analyzing a protocol, blockchain protocol, corresponds to defining the property of a mechanism. Then, second thing that we need, the analysis of blockchain robustness is done by considering 3 types of users acting differently when faced with a prescribed protocol. This model is the famous bar model, well known in distributed system theory. Altruistic users, so the one in green, follow the protocol no matter what happened. On the other hand, Byzantine ones, that are in red, arbitrarily deviate from the protocol. At the end, rational users, the blue one, may follow or deviate, depend on their utility. So they merely act to maximize their utility function. Okay. After defining a mechanism and the type of users, we can now model robustness as a combination of 2 properties: resiliency and immunity. Resiliency defines the maximum number K of rational players allowed in a game such that the protocol still provides the same utility to altruistic players. Immunity, on the other hand, defines the maximum number T of Byzantine players allowed in a game such that the altruistic players always get at least the utility of the initial state. We can see that the latter is a very strong property utterly satisfied by protocols. That is why we propose a weaker version of this property called T-weak immunity, defining actually the maximum number of deviation the game can have, not letting other players facing negative outcomes. Now, with these properties and numbers, K and T, so indicator, indices, we have a way to evaluate the robustness of different blockchain systems and to measure it with numerical values. So we did it for important blockchain systems, so for Ethereum and Bitcoin that are called layer 1 protocols, then for Lightning Network and Platypus that are layer 2 protocols, and finally we did that for a cross-chain protocol, in this case cross-chain swap. We have different values as the protocols are characterized by different we have different values as blockchain systems are characterized by different blockchain protocol that model their data structure, their consensus and communication network. All of these are really different among each other. Okay, now I would like to show you an interesting robustness analysis. That is the one we made for cross-chain swap. This particular protocol involving two different blockchain and allowing two different players, so users of two different blockchain to interact. Two players aiming to swap two crypto assets living on two different blockchains are called to play two separate games corresponding to two different mechanisms. These two mechanisms can be analyzed and their robustness level can be assessed with the properties that we presented before, just small manipulation on them. So, okay, now I won't enter into the detail of the protocol, but in the end, so protocol, of course, is complicated and transactions are locked and then unlocked, and several instructions need to be followed by the players involved in the swap. So we can see that here we have the two game 1 Bitcoin game and game 2 this altcoin game. So the two chains are the Bitcoin and the altcoin one. What is important to notice is that thanks to our modeling we can separately analyze the two games and define the robustness of the game's composition. So the composed mechanisms representing the cross-chain swap protocol is resilient and weak immune. And this is a theorem that we proved in our work. Okay, now to conclude, let me summarize what the contribution is about. The contribution provides a modelization combining game theory and distributed theory to measure the robustness of different blockchain systems. So what will be the next steps? Next steps will be the analysis of other, perhaps new blockchain protocols that will be defined in the following years, extending the model then to different actions and behavior, and introduce perhaps a stochastic component to the analysis. So thank you for your attention and hope to see you in the conference. Bye-bye.